Derivatives are very versatile, both in math and in the real world. In math, they typically find the slope of a function but can also be used for many other things, like relative extrema, points of inflection, and concavity, and so on. In the real world, derivatives are used for rate of change and a mathematical function.
One example of this is the position function. The position function measures movement of someone or something in respect to two directions on a basic xy graph. For example, the position function of a football punt would be graphed as a tall and fairly slim parabola, where x would measure distance moved on the ground, and y would measure distance moved vertically.
The first derivative of this function would find the velocity of the function at a given time, and is in units of distance per unit of time. The first derivative of this particular function would find that the velocity of the ball was fairly steady throughout the punt with respect to x, but variable with respect to y. As the ball climbed, the velocity was positive but slowly decreasing until it reached its maximum height, at which point the velocity was zero. For that point to where it hit the ground, the football's velocity would be negative because it is going down, or in the negative direction on the y-axis, and is gaining speed because of gravity.
The second derivative of the position function measures the rate of change in velocity, otherwise known as acceleration. When considering the football punt example, the slope of the ball's acceleration would be a negative constant because other than the initial force of the punt, gravity was the only force exerted on the ball throughout the ball's entire flight. A better example would be to find the acceleration of the punt with respect to ground distance traveled, because air resistance, loss of velocity, and other factors would steadily decline the ball's velocity with respect to x in a nonlinear fashion.
The third and final derivative of the position function measures the rate of change in acceleration and is typically called jerk, but is also known as surge, lurch, and jolt. I like to picture the acceleration of a scooter as compared to the acceleration of a drag race car to visualize jerk. Both could accelerate from 0 to 60 miles an hour, but where the scooter is going to have very slow acceleration and thus very low jerk, the drag car would have extremely fast acceleration and consequently more jerk.
To visualize these derivatives of the position function, we've recorded Reggie bowling. If you watch as he goes through his approach, you can see all four steps of the position function. If you were to call movement down the approach the x-axis and movement up and down the approach the y-axis, then you could graph the movement of the ball from where he starts to where he releases it as a position function. This position function can then be derived to find the velocity of the ball's movement at any given time. The derivative of the speed at that moment could then be used to find the ball's acceleration, which is very slow as he takes it back and very fast as he swings through to his release.
We can't pinpoint exact values or data because it is hard to record the speed of the ball as I am approaching my release and will require extremely expensive equipment. We can, however, find the average acceleration of the ball from the top of my swing to my release by knowing that my final ball speed is usually around 14 to 16 miles per hour. We'll say this ball traveled at 15 miles per hour to simplify things. By timing my release, we can conclude that in half a second from the top to the release, the ball went from 0 to 15 miles per hour. If you set that as 30 miles per hour per second, you can use conversion factors to find an average acceleration during this time as 44 feet per second squared.
To visualize another example of these derivatives, we can watch the ball curve as it goes down the lane. If you were to call the width of the lane y and the length of the lane x, the graph of the position function of the ball would look like a gently sloped exponential function. The derivative of this function with respect to y would find the angle at which the ball is moving down the lane at the specified time, and would also find the velocity of the ball with respect to y. The next derivative would then find the rate of change and the angle the ball is approaching the pins at. This would also find the rate of change in velocity, the acceleration of the ball with respect to y. As the ball is curving more and more while it rolls down the lane, the velocity with respect to y is accelerating because the ball is continually increasing the amount that it curves. The third and final derivative of this position function would find the jerk of the ball's curve. If you watch the beginning of the tape, the ball has little to no curve. As it travels, however, the acceleration increases steadily as the ball curves more and more. Picture a car with a lot of power peeling out. Initially, the acceleration will be very slow because the tires are spinning and the car has very little change in position. As the tires, or bowling ball, start to grip, however, that acceleration is going to rise at a steadily increasing rate. The jerk of the function will measure the rate at which the acceleration is increasing.